This lecture is on rational functions, features of them, and graphs of rational functions. A rational function is a quotient of two polynomials, so this rational function f of x would be n of x over d of x, the numerator polynomial divided by the denominator polynomial, and of course it's not defined when you're dividing by 0. The simplest type you'd find is f of x equals 1 over x. This is the basic look of f of x equals 1 over x. We have a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. Here's our domain, everything but 0, range is everything but 0, no intercepts. We can see it's odd, it's symmetric about the origin, then here's the asymptotes again. Now, finding vertical asymptotes you may be familiar with, horizontal not so much. To find vertical asymptotes, basically we would notice that as we approach a certain x value, our y value is either going to positive or negative infinity. Horizontal asymptotes is the opposite, that is, as x is approaching positive or negative infinity, we're approaching a fixed y value, and we'll look at some examples of that in a moment. Here we have a way to try to find these asymptotes. Here's our rational function n of x over d of x, numerator over denominator. This is some polynomial with degree n. This is a polynomial degree m. The graph will have no vertical asymptotes if the degree of the numerator is higher than the degree of the denominator. That's this last part here. If the degree of the numerator is less than the degree of the denominator, we will have y equals 0 will be the horizontal asymptote. That is the x-axis. And finally, if this degree of the numerator and denominator are the same, then our horizontal asymptote will be the quotient of the leading coefficients, unless you have a hole, which again we'll get to in a little while. They mention having no common factors. That's where you're going to get holes, as you'll see. So basic examples of finding vertical and horizontal asymptotes. For this example, no vertical asymptotes because 3x squared plus 1 will never be 0. Horizontal asymptote will be at y equals 0 because the numerator is less degree than the denominator, lower degree. In B, we have vertical asymptotes at x is plus or minus 1 because if you set the denominator equal to 0, you get plus or minus 1 for x. And horizontal asymptote at y equals 2 because the degrees are the same for the numerator and denominator, so you look at the leading coefficients, 2 divided by 1. Sometimes you have multiple horizontal asymptotes, and that can be a little bit more confusing. So here's an example with multiple horizontal asymptotes. You have to think about whether you're going to positive infinity or negative infinity. If you're going to positive infinity, that is x going to positive infinity, absolute value of x is the same as x because you're positive, and we have x plus 10 over x plus 2, and so therefore we just have 1 over 1, so y equals 1 is our horizontal asymptote. If we're going to negative infinity, well, now the denominator is basically, because of this absolute value, we'd have negative on top because we're going to negative infinity with positive on the bottom, so negative over positive is positive, so we have y equals negative 1 as we go to the left, and so we can see the graph as it goes towards the left, it approaches y as negative 1. As it goes towards the right, it approaches y is equal to positive 1. Here again is a summary of some of that information from the book. F of x equals p of x over q of x. Now I'm using those the functions instead. So for a vertical asymptote, you set q of x equal to 0, and we have to assume p of x is not equal to 0 because then we have issues with holes. To find a horizontal asymptote, you find the limit as x approaches plus or minus infinity of f of x. What this means, calculus term, is imagine x gets very, very big positive, very, very big negative, and see if f of x gets to a fixed value, and if it does, that will be your horizontal asymptote. And finally, oblique asymptotes or slant is when p of x is 1 degree higher than q of x, and if that's the case, you divide the two using long division or sometimes synthetic division, and whatever your quotient is the asymptote unless the remainder is 0, and then you're going to have a hole. Now, one of the newer parts of this for pre-calculus students is evaluating these limits to find horizontal asymptotes. So here's a generalization of it. Here we have again ax to the nth over bx to the nth is our leading terms. If this is the case as x goes to infinity, we can ignore the lower degree terms and we're just left with ax to the n over bx to the n, which becomes a over b. Here's the equation of our horizontal asymptote. If the degree of the numerator is less than the denominator, then we have something very big on top but much bigger on the bottom, and our limit ends up being 0 as x approaches infinity, so therefore our horizontal asymptote is y equals 0. And if the numerator is a higher degree than the denominator, again we can ignore all the lower degree terms. We end up getting infinity for our limit. It's possible we have an oblique, but we definitely do not have a horizontal asymptote. Here are a couple examples with graphs. So here we have y equals x squared minus x over x plus 1. I can factor the numerator. In doing that, it helps me to find x-intercept. So I have an x-intercept at 0 and at 1, hence those 2 points. I have a vertical asymptote at x equals -1 because of the denominator. Now this slant asymptote, let's see where that came from. The degree of the numerator is 1 more than the degree of the denominator, and so I can divide. I chose to use synthetic division, so the x plus 1 gives me a -1, x squared minus x, here's my 1x squared minus x, and then 0. Doing synthetic division, I have a remainder of 2, so it's a non-zero remainder. So therefore, when you divide, you get x minus 2 plus 2 over x plus 1. Now again, if we were to imagine x getting very, very large, 2 over x plus 1 goes away, and so our graph would be approaching y equals x minus 2, which is why that would be our slant asymptote. So here we have our vertical asymptote, our slant, we have these 2 points, and then we draw in the graph accordingly. It would seem, before you draw the graph, that you don't have enough information to do it, but we know that the graph cannot be at here because it doesn't cross the x-axis anywhere but these 2 spots. Same reasoning, it can't be over here, which leads us to the conclusion that we have a piece in here and we have a piece over here. And there's other calculus techniques you can use to verify that. Here's another example. This rational function x over x squared minus x minus 2. I can factor the denominator, and I have vertical asymptotes at -1 and +2. Because the degree of the numerator is less than the degree of the denominator, I have a horizontal asymptote at y equals 0, hence this red dashed line. If x is 0, y is 0, so that's 1 point. So now as far as getting the rest of the graph, well, if x is bigger than 2, like say 5, then I would have a numerator which is positive, a denominator which is also positive. Positive divided by positive is positive, so I know I'm in here somewhere. I don't cross the x-axis at any place but this spot. I know I'm approaching the asymptotes, and I'm over here. Therefore, I have a curve which looks like this. On the left side, if x is, say, I don't know, -20, I would have negative on top, negative, and negative here. So negative divided by negative is negative. So therefore, if I go to the left, I should be down below the x-axis, so I have a piece down here, and didn't mean to hit my asymptote here. Now in between, if x is a little bit less than 2, I'll have positive here, and slightly positive here. If it's if a little less than 2, I'll have slightly negative, so positive, and a little negative, which would mean I'll be negative, so I'm going to be down here. And then, as you can imagine, I'll be in this spot. So if x is a little bit above -1, this will be positive, this will be negative, and this will also be, let's see, a little less than -1, so negative, say 0.99 plus 1 is positive. So I'll have negative on top, and then positive and negative, so that's a positive, and so I know I'll be up this way. So there's my graph. So you get some asymptotes and some intercepts, and think about bigger or smaller, negative, positive, and you can get quite a detailed graph just from that. So that's with asymptotes. Let's take a look at the situation with the whole. X squared minus 4x plus 4 over x minus 2. Initially it looks like we have a vertical asymptote at x equals 2, and we check for a slant asymptote. When we do so, we divide and we get a remainder of 0. So really what happens is, this is just exactly the same as the line y equals x minus 2, because actually if we were to factor the numerator, we get x minus 2 squared, we can cancel them. It's the same as y equals x minus 2, except because x can't actually equal 2, it's this blue line with the red hole there. So it looks just like y equals x minus 2, except you do have a hole in your graph, a discontinuity.